So for the first session, we have Professor Nam Quang Lee, if my pronunciation is correct, from Indiana University at Bloomington. He's an expert in partial differential equations, geometric analysis, and the calculus of variations. And for today, he is going to talk about variational problems with a convexity constraint and twisted Harnack inequality. So please, Professor.
Good morning. Thank you very much for the introduction. It's my great honor to be invited to speak at the ICBS. I would like to thank the organizer for the opportunity and for the online accommodation. So yes, I will talk about variational problems with a convexity constraint and a twisted Harnack inequality. So this is the brief outline of my talk. I will mention a couple examples about the calculus of variation with convexity constraint. Then I will introduce the idea of approximating the minimizers by singular Abel equation, and the equation comes from complex geometry. Then I will discuss the solvability of singular Abel equation, and then I will mention a key tool in the analysis, the twisted Harnack inequalities. And then if time permits, I will talk about the ideas and the heuristics. Let's start with the calculus of variation with convexity constraints. The idea is to minimize certain functional for I among the competitors, which are function with certain convexity conditions on some domain omega in Rn. So with the convexity condition on the competitors, we are imposing certain higher order or geometric condition on the competitors. Because for convex function, one condition is that the Hessian matrix must be in a negative definite. So if we look at this kind of variational problem with a convexity constraint, the basic question is, what information can we obtain from a minimizer? The information can be analytics, such as the Euler-Lagrange equation, or the information can be geometric, or the information can be about the approximation properties if we care about numerical methods. So let's start with some motivation to see that this kind of problem is quite different from the usual calculus operation. Let's look at the case of the Dirichlet energy functional, and we minimize the Dirichlet energy functional over the set K2, the set of all convex function in the domain omega with a fixed boundary value phi. All right. So because of the convexity constraint, we could not just do any kind of perturbation in any direction, but we had to be a little bit more specific. So the only way we can do is to do the perturbation in the form of U plus dV, where V is a convex function vanishing on the boundary, and this may keep the boundary data. And on the other hand, to keep the convexity, we have to impose that T positive, because when T is negative, U plus dV may be non-convex. All right. So with this information, we compare the energy between U plus dV and U, because U is a minimizer, then the energy evaluated at U plus dV is not smaller than the energy evaluated at U. And so this information, and we divide by 2t, and so by a simple calculation, we got the expression which is non-negative. All right, so then we let t go to 0, then we get these inequalities. And so this is the quadratic form involving the gradient. And so this is familiar, but the point is we don't have the equalities, we have inequalities. And so if we integrate by part and keep it in mind that v is 0 on the boundary, then we have this form, and we see that the appearance of the Laplace operator acting on U. Okay. And so this is an inequalities, and it works for all V convex vanishing on the boundary. And so the question is, what kind of Euler Lagrange equation for you. Without any convexity on the minimizer, clearly U is a harmonic function, so the Laplace of U equals 0. But in this case, because of the convexities, so what can we say about the Laplace of U? All right, so I rewrite the inequality we just wrote down before. So a while ago, Leon observed that in a standard distribution, negative Laplace of U is a double divergence of a metric of random measure. So let's call that metric mu ij. And so mu ij, its entry is a random measure. And this metric is symmetric and is non-negative definite in the sense that if we test mu ij's again any non-negative definite matrix, we integrate over the domain omega, we have some quantity non-negative. All right. And so in the standard distribution, the expression above is expressed as follows. For any function w vanishing on the boundary and C2 in the domain omega, we have the expression minus Laplace of u times w equal the expression. And so we see that this is just a sanity check because when w is a convex function, then the Hessian of w is a negative definite, and so this expression here is clearly non-negative because of the information about mu ij. All right, so this is very interesting. It's quite different from the case of the calculus variation without any convexity built in. So the question is, what can we say about the metric mu? It turns out that in many cases, even in this case, the structure of this matrix is quite mysterious. And so therefore, we need to find a way to understand more or even to find some explicit approximation of this matrix and even for the minimizer. Okay, so that's the motivation for what I'm going to mention in a couple of minutes. All right. So it turns out that the calculus variation with convexity is severe in many settings, in many instances of sciences and economics. So in physics, we have the Newton problem of minimal resistance. And so this problem consists of minimizing this functional among all convex function u with boundary between two constant. The second instance arises in elasticity. In this case, when we describe the behavior of thin elastic cell, we end up with minimizing this functional. And so in this case, omega naught is the given domain in R2 and gamma is a given function. We need to minimize this functional among all function u, which is convex in the whole plane and is equal to this particular quadratic function outside the domain omega naught. And so this problem comes from elasticity. Another problem where we have the calculus variation with a convexity constraint comes from economics. So in this case, I would like to mention the monopolist problem. And so the idea is that the monopolist would like to design the product line at a price P to maximize the profits. And so the monopolist would like to calculate the total profits, called capital phi, and it's defined the difference between the selling price and the production cost. And the idea is to have the product and the price so as to have the maximal capital phi. So in general, this problem is complicated, but a while ago, Rose and Sonia observed that the total profit phi can be written as a function of the buyer utility function. And so the utility function, let's call it U, all right? And so what is the utility function in terms of the price and then the product line? So it turns out that the utility function is the convex dual of the price. So clearly, the utility function is convex. On the other hand, because if we would like to sell any product, the customer want to see the use of the product. So therefore, the utility function must be above certain threshold. And so therefore, there's also another constraint that the convex function u here must be above certain function phi. And so this is called the participation condition. So in the case of quadratic cost, rewriting the total profits in terms of the utility function give us this functional. And so this is the functional written on a domain omega naught in Rn. And so the significance of omega naught is that it's the collection of type of the agent, and gamma, the function gamma here, is the density of the type of customer having the preference x. And so what is the dimension n? The dimension n is the number of the key characteristics of a product. So let's say if we would like to buy an iPhone, we would like to see what is the size and what is the resolution and what is the memory. So that's all right. So all in all, in economics, we need to minimize this functional among all convex function u above a given function phi. And so this is another instance of the calculus operation with a convexity constraint. All right, so before moving on, I would like to mention that this functional is quite simple, but it had many interesting connections with other area of mathematics. So if we do the square completion, then we have this functional, and this functional is where the expression x minus du of x squared. So this is a familiar term in optimal transport, and actually this functional is closely related to a certain problem in optimal transport, and it has been analyzed by many mathematicians. On the other hand, in the Variational functional here, we have this term, and so x dot du, and so if we put du equal y, and so this is just a bilinear expression in terms of x and y. If instead of having the bilinear expression, we have some more general expression, and then this problem will also analyze, and it turns out it's connected to the anti-doubly condition in optimal transport, so that's the Marr-Thuringer-1 condition, and the analysis of this problem turns out to be related to Thuringer theory of generated Jacobian equation. And so this problem is interesting. Many of its variation and variant had connected to many areas of mathematics. On the other hand, if we just look at the regularity of the minimizer of this problem above this constraint, then it has been analyzed by many mathematicians. So I would like to mention a couple of names and some recent work here. So my talk is not about the regularity of minimizer, but about the approximation of the minimizer. And so as such, I would like to make some connection with the problem in elasticity. And of course, there are many aspects to consider, but I would like to consider one aspect that somehow lead to many interesting mathematics. And so as we saw before, our constraint is a convex function u above a threshold phi in a domain omega naught. So this is the functional again. So let's say that in the very special case that u is exactly phi on the boundary. And so somehow we can arrange the domain omega naught to be such. And so therefore, what can we do more in this situation? And so observe that. So let's say that this is the domain omega naught, and the function on top here is the function u, and the function with some corner here is the function phi. And so when they coincide on the boundary, and so therefore if we extend the function u by exactly phi outside the domain omega naught, then the extended function turns out to be globally convex. You can see from the picture. And so therefore, this leads us to a variational problem with a convexity constraint as follows. So we look at the Rosset-Sonnet functional, and we look at this constraint. The constraint is the following. It's the set K phi is the set of all convex function u, which is convex in the domain omega naught. And then when we extend by phi outside omega naught, it gives a global convex function. All right. And so this is the picture. So all the analysis work for general function gamma and with the low order term. However, to point out the key ingredient and the interesting aspect and some the features of the analysis, I would like to drop the lower order term and also put the function gamma, the density to be 1. But in the analysis, it works for all gamma ellipses. All right. So if we look at this kind of variational problem with a convexity, by the way, this is exactly similar to the problem in elasticity. The, the set of constraint is almost the same. All right. So if we would like to look at this problem, the variational problem with a convexity constraint, then we have encountered many difficulties. Analytically, the Euler-Lorentz equation are not easy to use or well understood. So as we saw the motivating example before, and numerically, it's very hard to handle the convexity in numerical schemes. And so therefore, we would like to see whether we can approximate minimizers and the Euler-Lorentz equation by some higher order equation. So that's the question that I'm interested in. All right, so how can we do the approximation? So there are two levels. Because we have a functional, and so let's start with the functional level. And so let's say that this is our original functional, and this is our convexity constraint. And so the idea is that we add some new terms, and the new term will penalize if we are far away from the constraint. And so the first term is that we want our function to be close to phi when we are outside omega naught. So it's natural to add this term, and we divide by 2 epsilon. The idea is that when epsilon is small and if the whole thing here is bounded, then the boundedness of this term, the second term here, forces yield very close to phi. And now, in the constraint set K phi, we had the convexity of the function u, and the convexity is on the whole domain omega, and so therefore we would like to add this term log determinant of the Hessian. The idea is that if we want to compute log of the determinant of the Hessian, then the determinant of the Hessian must be positive, and so therefore a very natural candidate for that is u to be convex. And so you might wonder why I have the negative sign in front of this integral here. The idea is that if we add this term, the second term, to penalize u being far away from phi, actually this term gives a convex functional. So, but the log determinant of the Hessian turns out to be a concave functional in the cones of positive definite matrices, and so therefore the negative term here makes the new functional to be convex. So we want to have a convex perturbation. And so this kind of perturbation has some flavor in many other settings, such as the Gilbert-Landau approximation of harmonic maps into sphere, or the Alenkern approximation in phase transition. And so this is the functional level. And so somehow when writing this new functional, we would like to ignore the constraint we are dealing with because the constraint seems to be difficult to handle. And so what can we do? The idea is that maybe we should look at the critical point of the functional and solve the equation, and somehow when letting epsilon go to 0, we can recover the minimizer of our original variational problem. Okay, and so now let's look at the critical points of the approximating functional. What can we obtain? So if we take the variation of the log determinant, we have the expression on the left-hand side here. So if we take the derivative of log, then we have 1 over x. So therefore, it's natural to see the term, the inverse of the determinant of the Hessian. On the other hand, when we do the variation, we also take the linearization of the Monson-Bell operator. And so therefore, this expression capital Uij. And so this is this matrix here is the cofactor matrix of the Hessian of U. And so this is the variation of the term log of the determinant of the Hessian. On the other hand, if we look at the dirichlet term in the domain omega naught here, this gives us negative Laplace of U. And if we take this term, we do the variation, we get this expression. All right. And so this is when we do the the variation, we don't have to worry about any about the convexity or anything about the constraint. All right. And so it turns out that the left hand side here appears in many other settings, such as in the upper equation in complex geometry. And so I will mention more about this equation. So in complex geometry, we saw this expression on the left-hand side, but the right-hand side in that setting is a given smooth function. However, in our situation, we look at the right-hand side. The right-hand side involved also the unknown function u. And so, but when u is convex, if without any further information, then Laplace of u is just a random measure, a negative random measure, and so therefore this term can be in fact singular, and so therefore we put everything together, the upper equation on the left hand side and the singular term on the right hand side, so that's we call this the equation called singular upper equation. So that's the terminology. It's not quite correct. Anyway, so I mentioned before, our left-hand side is the upper equation in complex geometry. So this is the upper equation appears in the works of Donaldson in the infinite ectomometric ontoric manifolds. There's another way to write the upper equation. So we can rewrite the expression on the left-hand side as the double divergence of the inverse of the Hessian matrix. In this equation, we see that the exponent here is -1. If we change this number, this exponent from -1 to negative n plus 1 over n plus 2, then this equation actually turns out to be the affine mean curvature equation in affine geometry. And so our problem has many connections with geometric context, although our motivation first came from elasticity and also the economics. All right, so we will work with the upper equation a lot, and so I would like to spend some time talking about it. So if we look at this equation, clearly we need two derivatives to compute this expression, and we need to compute two more derivatives. So therefore, this equation is a fourth order equation. Because of this expression, somehow we can rewrite our upper equation in terms of a system of two second order PDE. So if we put W equal the inverse of the determinant of the Hessian, then we obtain this equation. And so this is a fourth order PDE written as a system of two second order PDE. The first one, this one, is a Monod equation for U in terms of determinant of the Hessian of U is equal the inverse of W. On the other hand, this equation as an equation for W is a linear Monod equation for W because the coefficient metric capital Uij come from linearizing the Monod operator. So here, if we linearize the Monod operator in the direction of the function v, so if we do this expression determinant of the Hessian of u plus d square of v, we do this expansion, and then we look at the coefficient of t, and the coefficient of t is very similar to the expression on the left-hand side here. All right, so in general, the mathematical factors, capital Uij, is very complicated in high dimension, but in two dimension, it has a very simple expression. So this is the Monod operator in two dimension, and if we compute the mathematical factors in two dimension, it has very simple expression here. So as mentioned before, this upper equation comes from taking the critical point of the approximating functional, and we would like to look at this equation, and we would like to solve it with certain boundary data, and we hope that the solution will approximate the minimizer of our original functional. So because our equation here is a system of two second order PDE, one is an equation for U, another equation for W. So if we would like to impose the boundary condition, it's natural to impose boundary condition for U and for W. And so for U, that's very familiar, but if we impose the boundary data for W, so we are imposing the determinant variation of U on the boundary. And so therefore, this is called the second boundary value problem. It is different from the first boundary value problem where we impose the boundary data for U and the gradient of U. Here, we would like to impose the information for U and W on the boundary. And so this is what we are going to do. And so the first equation is nothing but our equation written in terms of U and W. On the other hand, we would like to impose what kind of boundary data we want to impose for U epsilon here. So as we can imagine, we would like in the end U epsilon to recover the minimizer, but our minimizer belongs to the constraint set. And so it is given by phi outside the domain omega naught, and it is convex in the whole domain omega. And so therefore it's natural to put U epsilon to be the function phi. On the other hand, what can we put for the Hessian determinant? It turns out that we can put any positive function on the boundary, and we don't have any constraint on side. All right, and so this is, we would like to see whether we can solve this equation, and when we can solve it, whether U epsilon will tend to the minimizer of our original variational problem. It turns out to be the case in all dimensions. And so let me mention the key theorem. In this approximation theorem, whenever epsilon is small, then the above equation had a uniformly convex solution U epsilon in W4S for all S bigger than the dimension. And so here, so U is uniformly convex and had four derivatives, and the fourth derivative of U belong to Ls for all S finite bigger than the dimension. And so somehow we would like to point out that we don't expect the solution to this equation to be C4. The reason is that if U epsilon is C4, then the left-hand side give us a continuous function. However, if we look at the expression on the right-hand side, we might have some potential jump across the boundary of omega naught. So we don't expect to have a C4 solution for this problem. Maybe we can expect to have a W for infinity, and it turns out to be the case in one dimension, but it's not known whether we can do that in the dimension 2 and above. So now we can solve this equation for any psi. So this is something amazing. And furthermore, whatever psi we choose, then when epsilon tends to 0, then we can show that U epsilon converges locally, uniformly to the unit minimizer of this energy functional with this convexity constraint. And so somehow this theorem says that the solution to this equation actually recover the unit minimizer of our variational problem with the convexity constraint. So there's a long history of solving of proving this theorem. It started from two-dimensional case in maybe in CPAM, and for this directly energy, and after that with Binzo, we were able to manage to do the case when this energy is replaced by the Q Laplace energy. And so for all Q bigger than 1. And then for all dimension, from 2 and above, it was done in the recent paper in advance. And so somehow, although I wrote this functional to for simplicity, but actually the analysis of this kind of equation also work for the Rosset functional. And so therefore, we can say that minimizer of the Rosset functional in economics can be approximated by solution of the singular Appler equation in complex geometry. And so somehow this theorem tied up two fields, economics and complex geometry. All right, so this theorem is about approximating the minimizer of the variational problem with a convexity constraint. And so what about the Euler-Laurent equation? Because as we saw before, the Euler-Laurent equation for variational problem with convexity constraint can be very complicated. Anyways, for this kind of problem, we can expect that the minimizer satisfies this Euler-Laurent equation as solved by Leon. And so we don't know what can we say about the matrix of mu ij, except that it's a symmetric matrix. All right. And so let's say that it turns out that we can make some connection of the matrix mu ij with the solution u epsilon, the approximating solution we just found. So here's how. Remember that this is our approximation problem. And so theoretically, the expression on the right-hand side here resemble this expression. And it turns out that because u epsilon is convex and converges locally uniformly to u, then this expression here converts to minus Laplace of u in a sense of distribution. And so we are good with the right-hand side. We don't have to worry about what happened outside omega naught. And so on the other hand, if we look at the expression on the left-hand side here, we can rewrite by a simple argument, we can rewrite this expression as the double divergence of the inverse of the Hessian of u epsilon weighted by the weight epsilon. And so therefore, if we look at this left-hand side and this expression, we can think that the epsilon times the inverse of the Hessian of u epsilon as an approximation of the matrix mu. And so therefore, somehow before we don't know much about the structure of mu, but now it seems that mu can be approximated by a single matrix, and the matrix is the inverse of the Hessian of the solution to this singular Abler equation. And so this is a conjecture. It turns out that it is true in one dimension by the work of my PhD student, Young Ho Kim. However, it's widely open in high dimension. We don't know whether we can make this rigorous in higher dimension. And so somehow we see that solving the second boundary value problem for singular Abler equation give us the minimizer of the variational problem with the convexity constraint, and it also give us a conjectural picture about how to approximate the matrix mu in the Euler-Laurent equation. All right, so we saw the usefulness of solving the singular Abler equation, and so how to solve that. All right, and so if we look at the Abler equation with a given right-hand side f, if f is smooth or has certain integrability, then the second boundary value problem can be solved from the work of many authors listed here. However, less you know when the right-hand side is singular, and that's the case that we are dealing with, because in our case, the right-hand side is not given, but it depends on the unknown also. Before going further, let me mention how to solve this kind of singular Abler equation. So I put epsilon to be 1 because from now on, epsilon will not play an important role because we are solving the equation. And so let's scale everything. And so we look at this singular Abler equation with bounded data for u and the Hessian determinant of u. And so the idea to solve this equation is to use the degree theory and a priori estimates. The point is to obtain for derivative estimate for the potential smooth solution u. And so in terms of the data is the dimension and the sovereign exponent s, the boundary data phi and psi, and the domain omega naught and omega. And so in order to obtain this fourth order derivative estimate, there are two key steps. The first step is to obtain the Hessian determinant bound. So we would like to bound the Hessian determinant of u, bounded from above and below. This is more or less standard by using certain maximum time argument, maximum principal argument, and Legendre transform. So this can be done. However, the major difficulty is to get better regularity beyond this inequality. And so the key is to obtain the global holder estimate for W. And so why that's important? Because when we obtain that, let's say that W is globally C alpha, then we look at this Monson equation and we see that we have determinant Hessian of U equals a globally C alpha function. And so by using an important result of Turing going 1, we can show that U had two more derivatives better than the right-hand side. So U in C2 alpha globally. One U is C2 alpha, we look at this expression on the left-hand side here. We, of course, this right-hand side now is bounded by the data because U is equal to alpha. On the left-hand side, if we look at the mathematical factors, we see that these mathematical factors is now globally C alpha, and it is uniformly elliptic. And so therefore, by the standard Calderon-Zygmunt theory for the equation of W, we see that W belongs to W2S for OS finite. And so when W belongs to W2S, we look at the equation for U, and you had two more derivatives better than W, and so therefore U belongs to W4S, and we with the estimate here. And so therefore, the key point is to obtain the global holder estimate for W. And usually, in order to do that, we can usually do via the Harnack inequality. It turns out to be very challenging in this situation. The reason is that because our equation had two difficulties. The first one is the degeneracy of the linear Riemann-Rosenberg operator given only this information that the bound on the Hessian determinant of U. And on the other hand, if we look at the right-hand side, the right-hand side have very low integrability. So I will explain a little bit more about this. All right. So the equation for W in our upper equation is a linear Riemann-Rosenberg equation. So the linear Riemann-Rosenberg equation is written in this form, where capital Uij is the mathematical factors of the Hessian of U. And so this comes from linearizing the Riemann-Rosenberg operator. And so if we look at the expression, it turns out that the mathematical factors is divergent free. So it means that if we take the divergence of each row or each column, we get 0. And so therefore we can rewrite the expression on the middle term from non-divergent form into divergent form. Because whenever we take any derivative on U, we land derivative here, they can cancel. So the effect only on V. If we look at this linear Riemann-Rosenberg equation with this information, that we only have the control on the bound on the determinant of the Hessian of U, then in general, we have no control on the eigenvalues of the matrix capital U here. The only thing we can control is that we can control the product of the eigenvalue of the coefficient, because the product of the eigenvalue is exactly determinant of the matrix capital U, and the determinant of the matrix capital U from the expression is just the m-1 power of the determinant of Hessian of U, but because we have the bound on the determinant of Hessian of U, so we have the bound of this expression, and so therefore we can control the determinant of the matrix capital U. So in the classical theory of uniformly elliptic equation, we have the coefficient matrix with eigenvalue bounded from above and below. But in this case, we don't have the bound from below and above, but we can only have the bound from above and below of the products of the eigenvalues. And so this is one of the major difficulty in working with the linear Riemann-Rosenberg equation. On the other hand, the linear Riemann-Rosenberg equation is invariant under unimodular transformation, in the sense that if we transform the equation using a linear transformation with determinant 1, and then the equation is invariant, and so therefore we have a larger group of invariant. And so therefore, if we would like to work with this linear Riemann-Rosenberg equation, we could not work with just Euclidean balls, but we have to work with objects that are invariant under unimodular transformation. And the objects are sort of ellipsoids or ellipsoid-like. For the linear Riemann-Rosenberg equation, they are just sublevel set of the function U, right? And so moving ahead, I would like to mention that therefore the analysis of the linear monotone equation involves many arguments on involving harmonic analysis on homogeneous spaces, and we could not work with distance, we could have to work with quasi-distance. So anyway, there's a quick comparison between linear monotone equation with the classical theory. So let's say that we work even with the trip term. Then if we look at the non-divergent form of the linear monotone equation, then from the work of many authors, so far we have a very good understanding of the non-divergent form of the linear monotone equation, and they are comparable to those of the classical theory. Especially if we would like to do the Harnack inequalities, the best thing we can do is that we need f to be at least in Ln over 2. And so we have the integrability at least half of the dimension. On the other hand, if we would like to consider the divergent form of the linear monotone operator, then somehow we have a very good understanding in 2 dimensions, but in high dimension, it's still mysterious, and there are some results, but somehow the result always involve certain integrability condition of the Hessian of the potential function u, or some information about the vector field f weighted by the Hessian of u. And so if we look at singular Abel equation, so if we look at this term minus Laplace of u, we can also write as the divergence of the gradient of u. And so therefore, this equation we can analyze either in terms of the non-divergent form or divergent form. But because we don't have a good understanding of the divergent form of the linear monotone equation in high dimension, and so therefore, if we would like to have any chance of success in solving the singular Abel equation, we should work with the non-divergent form. Anyway, that's the trouble with the left-hand side. Now, on the right-hand side, given this bound, we also have the trouble on the right-hand side. Because if we would like to work with the non-divergent form of this singular Abel equation, we would like the right-hand side to have integrability at least half of the dimension. It turns out that's the only valid in 2 dimensions, but not in higher dimension. Because with this bound, we can obtain by many other methods, then we see that what can we say about the integrability of the Hessian of u? There were very important results by the Philippis, Figali, and Savin, and also by Smith, and that's the interior result, and at the boundary by Savin, saying that the Hessian of u under the condition belong to L1 plus epsilon for some very small epsilon. And the epsilon here depends on the dimension and little lambda, capital lambda. And so when d bound, little lambda, and capital lambda are far apart, the integrability can deteriorate. So in the sense that epsilon here can go to 0 when this ratio go to infinity. And so therefore, in general, if we look at the integrability of the Laplace of u or the Hessian of u, we see that it's just better than L1, but not more. And so therefore, if we are in dimension 3 and above, the integrability could not be bigger than dimension divided by 2. And so therefore, we got trouble if we want to use the divergent form, non-divergent form of this singular Abel equation. All right, so the only encouraging news so far beyond the bound on the Hessian of u is that we also have the global C1 alpha under the condition and the 9 boundary data. So this is the result by Savin and I. And so U is C1 alpha. That's the global result for the monotone equation. Global C1 alpha. All right, so now how to solve this kind of equation, because we see that if we would like to handle this term, we could not just leave it there. We have somehow to have to remove it because it has low integrability. And so it turns out that the first step is that if we have singularity in the whole domain, then that can be done. And so let me mention the first progress on handling the singularity on the right-hand side. And suppose that the omega naught here is exactly omega, then we have this kind of singular Abel equation. So it turns out that we can do it for all f with certain integrability because we can remove the singularity on the lower integrability, so we can remove the Laplace term on the right-hand side. And so, first of all, I would like to mention that by whenever f here it had this integrability by using a trick by Zhao and Weigel using ABB estimate, we can obtain an upper bound for the Hessian determinant of U, and after that, using Legendre transform, we can have a lower bound. And so we are in the setting here. All right. And so now we would like to remove this term. And so it turns out that we can introduce a multiplier. The multiplier called to the power du squared over 2. Recall that we know that U is C1 alpha globally, and so this expression here, the multiplier here, is actually C alpha globally. And so if we look at, we multiply this multiplier with W to get an expression eta, it turns out that eta solve a linear Monson equation with a trip. But now we look at the trip, we have already the bound on this term via the estimate mentioned above, but du is also bounded because u is C1 alpha. And so therefore we have a linear Monson equation with bounded trip, and the integrability of the right-hand side is the integrability of f. And so because of this transformation, and the transformation is via a Holder continuous expression. So if eta is Holder, then so is W. And so therefore we need to prove the Holder regularity for this equation. So in the interior, that's not an issue because one of my old papers, I proved the interior Harnack inequality for linear Monson equation with bounded trip and Ln right-hand side. And here the right-hand side is even better than Ln, is the Ln 2n plus. All right. However, as mentioned before, if we want to solve this equation, we need to obtain the global Holder for W. And so therefore, at the boundary, we need to obtain the Holder estimate for W. However, we got trouble because we don't know how to do that. When f is not bounded, when f is bounded, there's a way to handle that. But when f is not bounded, we don't know how to do it. So this leads us to find a new strategy. It turns out the strategy is very interesting. So somehow the trouble is that this term here is not zero. If at a point on the boundary, the trip term vanishes, then somehow we can prove the Holder estimate for the function eta around that point. And so therefore, at each point z on the boundary, we try to make the trip vanishes at the point z. And so instead of the original multiplier, we modify the multiplier. So this is the new multiplier. And so we obtain the new function eta z. And so the function eta z satisfies this linear Monson equation with trip. But this trip here vanishes at z. And from this, we can use some standard technique and with ABB estimates, and we can obtain the fact that eta z is Holder continuous at the point z. And so with the control norm. And so because eta z Holder, but the function u du is also Holder, so therefore we can obtain the Holder continuity of the function w at the point z. And we can do it for all the boundary points. And so somehow in this situation, we need to use a family of linear Monson equation. And so that's work for the case of the singularity in the whole domain. However, this argument does not work when we have the singularity it's just in the subdomain omega naught. And so this is exactly the situation where we need to solve the approximation problem. And so because if we use this multiplier, we can remove the singularity or the lower integrability in the domain omega naught, but we introduce the Laplace term outside omega naught. And so this term is again not in Ln over 2 when we are in dimension 3 and above. And so therefore, we got trouble. And so what can we do? It turns out that because we already have yield is C1 alpha, then for this term, yield minus phi, we can ignore it. So if we ignore this term, then we just look at this term, we see that the right-hand side of the equation for W actually had a sign, and so this is non-positive. On the other hand, if we do this transformation, we get an equation for eta. If we just ignore the lower order term, then the term Laplace of yield here is non-negative, and so therefore we change W here. W here is just super solution, but we change the solution eta into the eta, and eta had a subsolution property, and so therefore the point is we have this super and subsolution property, but we look at the trip is under control. And so therefore, if we can work with the equation with the trip and this kind of thing, then maybe there's some hope. And so the observation is that the equation for W and eta had definite sign in the domain omega. And so, of course, this is just heuristic idea, but we don't know how to make it further. So this leads us to the ideas of the twisted Harnack inequality. And so let me explain the idea for the case of the Laplace equation. It works for generally, but for simplicity, let me explain for the case of the Laplace equation. Suppose that we have the equation Laplace of v is called f, with no control on the integrability of f. And so f, we can imagine this on the right-hand side here. However, suppose that for each point z in the domain omega, we can find positive Holder continuous function, capital AZ, little az, both equal to 1 at the point z. And so somehow we twist the function v into new function capital Vz and little vz. So we twist by multiplying v by capital Az and little az. After the multiplication, Vz become a super solution and little vz is a sub-solution. And so, but we had the trip B, the vector field B, and we had the right-hand side. And suppose that for some reason we can control all the trip Bz, little bz, capital Bz, fz, and little fz. And so, suppose this is possible, then what can we say? So somehow we start with an equation. After multiplying by a Holder continuous function, we change the nature of the equation from the equation into super solution, and another change, we get a sub-solution, and so we change the nature of the solution, so this is called twist. This is the term, we don't have any better term. But anyway, the idea is that up to Holder continuous correction, V is a solution to the Laplace equation with bounded trip and bounded right-hand side. However, if we look at the Harnack inequality is a local statement. And so therefore, if we can do the Holder continuous correction, and the Holder continuous correction give us the bounded trip and bounded right-hand side, so maybe the Harnack inequality can carry out. And so so we can expect the whole Harnack inequality to hold for V. So initially, if we look at this equation with no control on the integrability of f, we don't expect to have any Harnack inequality for V. But if we can do the twisting, then there's some hope. And it turns out to be the case. And that's what done for uniformly elliptic equation or linear monotone equation, or even equation comparable to linear monotone equation in non-divergent form. And so somehow here, all the kind of this give us some kind of microscopic balances, and they give us some nice properties. All right, so I will, because of the time is almost up, so I will mention how to use the twist Harnack inequality in a singular Appler equation. And so let us recall that this singular Appler equation, we already have the lower bound and upper bound on the hash determinant yield, and yield is C1 alpha. And so if we look at the right-hand side, we see that W is already a simple solution, so we don't have to do anything. But Now we want to have a multiplier to make it as a sub-solution, because if we do this kind of multiplier, then the new function for each point z, we see that it satisfies this equation. We saw this equation before, so we change the integrability, the low integrability in the domain omega naught into the domain outside omega naught. And so this, because yield is convex, so this term we have the negative, and because yield is C1 alpha, so this term we have the good bound. And so therefore, under this kind of chain, and this is a holder chain, we see that WZ is a sub-solution. And so therefore, applying the twisted Harnack inequality, we obtain that we have the Harnack inequality for W, and this given W belongs to C alpha. And so this is the interior, but there's also an argument we do at the boundary. And so somehow the twisted Harnack inequalities saying that if at each point on the boundary or in the interior, we can have a multiplier, and the multiplier is exactly 1 at the point we are considering, and it's hold the continuous, and we change the solution nature from super solution to sub-solution, and then we can control all the trip, and we can control all the right-hand side. Then we have the Harnack inequalities. And so this gives us the global holder of W. And so the question is, for many equations, we don't have the twisted structure, but why for the singular Appler equation, we have the twisted structure? It turns out that we combine both structure. We look at the singular Appler equation, we use a non-divergent form. But when we do the multiplier, we twist the structure, we have to use the divergent form. The reason is that in the approximating functional, with epsilon equal 1 for simplicity, so this is the new term. And so this is the whole new functional. If we combine all the higher order term in the Lagrangian, so this term and the final term here, and so we combine the term, and so we have the expression inside the log. And we see that this expression inverse of the Hessian determinant is Rw, and this expression is nothing with a multiplier over here. So here. And so somehow we see that the analysis use both non-divergent form and divergent form of the singular Appler equation. The interesting point is that in the analysis, one, we can solve the singular Appler equation, then if this expression, we don't have the log determinant, but any concave functional in terms of the Hessian determinant, we can get the same approximating result. So U epsilon go to U locally uniformly, where U is the minimizer of the variational problem. So therefore, the question is whether if we replace this term by the determinant of the Hessian of U through some power theta, and theta is from 0 to 1 over n, so that makes similar to this term in terms of concavity. However, if we do that, we don't know how to solve the singular Appler equation, because we could not use we don't know how to find any good multiplier to do the structure. So in some of my recent work, it turns out that we can do that for certain classes of Bartle data, because that is very relevant to approximation, because previously we do for any psi. But psi, no matter what the value of psi, we can always have the convergence in this theorem. So, but now maybe if we change the log determinant by some concavity functional, maybe it's good to choose psi, and that's exactly the idea in some of my recent work. And I think I can stop here. Thank you very much for your attention.
Thank you for your talk. Any questions?
Hi, Nam. It's Tristan. I just have a question about the linearized margin pair Harnack inequalities. So if you instead relax the assumption on the lower bound, but say you know what the determinant is for some equation, then can you still prove some sort of Harnack inequality like this? Determinant to generating, but you know exactly how.
So thank you for the question. So in the setting of the this is the setting that I would like to I usually have. So your question is if you relax a little bit the upper bound or lower bound, or you have more information about the determinant variation. Is that your question? Okay, so somehow either if the determinant of the Hessian of U is very close to a constant, then of course there are better results. Beyond the Harnack inequality, we also have W1P, W2P for certain information about the variance IF. But on the other hand, if we relax the conditions, so if we put the determinant of the Hessian of U in terms of some measure, and if the measure is doubling, we also have the Harnack inequality from the work of Caffarelli, Guiccieri, and Maldonado. But other than that, we don't know anything.
I see. Okay, thanks.
Any other quick questions? If no, let's thank the speaker again.
Thank you very much.